Today we are going to talk about the idea of professional judgment, prediction, and qualitative exposure assessments. During the last lecture, we had discussed at length the AIHA exposure assessment strategy. And if you recall, it involves, first of all, a very detailed basic characterization of the workplace and the workers and the agents, followed by the classification of workers into similar exposure groups, and then a preliminary exposure assessment. And so today's lecture is going to be about how that preliminary exposure assessment is done in the absence of monitoring data. And as the title of this lecture indicates, it is going to be, first of all, qualitative, meaning without any measurements to back it up. And there's going to be a lot of professional judgment involved. So that's today's lecture. So, in the first part of my lecture today, I'm going to be talking about certain rules of thumb that have been developed in the profession to guide this initial assessment. And the other half of what I'm going to talk about in this first section is the idea of using checklists and why we need those. This first section of today's lecture is going to be about certain rules of thumb that have been developed in the profession that facilitate this initial exposure assessment and cut through the complexity, as I'll show you very quickly. And the second part is the use of checklists and why they are important in this first step. So, to give an example of how basic characterization might happen, I'm going to introduce you to a scenario where the exposure is to asbestos. And imagine that you are the industrial hygienist in this workplace and you are doing your initial walkthrough. Here, I call this asbestos scenario number 7 because later on in your homework assignment, you'll be assessing about 10 or 11 scenarios, and this is the 7th in that list. During this first go through the scenario, I will actually ask you to think about how you might go about doing this exposure assessment, but we'll not actually do it. It's just to illustrate the complexity of any modern workplace. So in this workplace, locomotive engine, steam engines are repaired, and the particular scenario is called locomotive steam line repair and air compressor removal and rewrap with asbestos. So the scenario is described as follows. An administrative assistant passes through the workshop while a railroad worker is conducting 3 maintenance tasks, all of which require removing and replacing woven lagging or tape that contains asbestos. Your exposure judgment should be based on the administrative assistant's inhalation exposure and not the railroad worker who's actually doing this task. And so, what is the administrative assistant's exposure, inhalation exposure to asbestos while he or she is in this workshop? The tasks that this administrative assistant does is essentially unrelated to the actual maintenance task. He or she delivers paperwork to a desk in the workshop, but at some distance away from the maintenance work, and we'll assume that the task duration is less than 30 minutes. So in terms of the environmental conditions, the maintenance was conducted in a large workshop that you see during your walkthrough. There is general mechanical ventilation, and you may not often know this, but let's assume that in this case you do know that the room volume is 14,800 cubic meters, and the exhaust volume capacities were not known but estimated. Based on an estimate of building volume of 14,800 cubic meters for the repair shop area, we basically estimate the air change rate within the building is 1 air change per hour with 1 fan on. And if you have 2 fans on, then you have 2.1 air changes per hour. And if you have 3 fans on, all three fans on, then you have 3.3 air changes per hour. And some additional information, again, this is more than what most industrial hygienists will have, but with all three overhead exhaust fans running, the airspeed is measured at about 23 feet per minute along the right side of the work area. So I will come back to the other part of it later on, because this is the airflow rate between the near field and far field. That is for a later modeling exercise that we'll come to. The agent itself, as I mentioned, is asbestos. The tape used to wrap the pipe contains asbestos. We know its CAS number. We don't really know much about the rate at which asbestos is becoming airborne, the generation rate. But based on the existing literature, the generation rates may be in the range of 0.001 to 0.1 milligrams per minute. So roughly 2 orders of magnitude uncertainty in that. And the permissible exposure limit, according to the California OSHA, is 1 fiber per cc. So you can see that when you sort of encounter this information, you don't really know how to begin to evaluate this all this information, and you don't really know what you should be focusing attention on. Although in this example, what I have done is, in fact, presented you what I think are the most relevant pieces of information. Typically, you would not, industrial hygienist is bombarded with all these sights and sounds, and it's a little bit more challenging to know what to focus your senses on in a real workplace. And the job of the industrial hygienist, as I described in previous lectures, is to use all of this information and make a preliminary assessment about the 95th percentile of the worker, in this case, the administrative assistant's exposure lies in. And so it could be in one of four exposure control categories. And just to briefly review it, if the 95th percentile of the administrative assistant's exposure profile is less than 10% of the occupational exposure limit, that's category 1. Category 2 is if the 95th percentile is between 10 and 50% of the OEL. Category 3 is the 95th percentile is between 50 and 100% of the OEL. And category 4, the 95th percentile exceeds the OEL. And for each one of these categories, then the industrial hygienist, after this assessment, can take appropriate actions. At this point, you can see that you as an industrial hygienist walked into this workplace. There's all these tasks going on, and you are really focusing not even on the person doing these tasks, but on a bystander, and are asked to evaluate that bystander's exposure. So you have to make this decision. And so at this point, I'm going to take a slight detour about decision making and professional judgment in a different context. I'm going to tell you a story of this Boeing Model 299. And this was developed sometime during World War II. And it was going to be the most advanced aircraft of its time. It had the latest technology, the latest everything, and Boeing had spent a lot of resources developing this. So finally, the day of reckoning came. The aircraft was going to take its maiden voyage. All the Air Force top generals and so on were there to witness this test. The top Boeing people were also there. And the flight took off, and almost immediately after going up, the plane crashed, stalled and crashed. And the Boeing company could have given up right at that point and said, okay, well, I don't know what's going on. But they did a very, very detailed review of the causes of failure. And what they realized was that unlike the previous aircraft, this one was an order of magnitude more complex. There were many more features. The pilot's dashboard had many more lights and flashing lights and buttons. So what turns out happened was the plane took off just fine, but after reaching a certain altitude, the pilot was supposed to turn on a switch that would bring back some tail flaps into a different position. And he essentially forgot to do that because there were so many things that he had to attend to at the same time. And it was, like I said, a very complicated, complex aircraft. And so that is essentially what happened during that air crash. And so what Boeing did, as after that lengthy review, they came up with a fairly straightforward solution, and they introduced a checklist. And the pilot had to go through each step and make sure he had checked off and done each step in the right sequence. And after that sort of simple fix, it was not a technological fix, but it's a fix to make us pay attention to everything in a sequential form. And so that was the fix. It was a checklist. The plane then flew many more missions after that, and it became one of the most well-known aircraft in the U.S. Air Force history, and eventually it became to be known as the B-17 bomber. And so the point of the story is that whenever you have any kind of complex series of tasks, human beings need a checklist. And this is not just true in this aircraft pilot's case. And certainly pilots, not just in the Air Force, but also commercial airline pilots use checklists all the time. But surgeons do it all the time. They have a checklist, so they make sure that they don't leave their scalpel inside a person after the surgery. And so it's a way to make sure that you don't do obvious mistakes. In the realm of industrial hygiene, we have developed a qualitative exposure assessment checklist. And this checklist is going to be used in conjunction with a series of rules of thumb that I'm going to be talking about today. And they need to be done in a particular sequence. And you also know, using this checklist, what to look for in the workplace. And so, like that example I showed you about the asbestos exposures, and you have a complex environment facing you, which parts of the environment should you focus your attention on that are truly driving the exposures? And which ones are just background information that you don't really need right away? So that's the goal of this. So we have certain rules of thumb, and we are going to use it in the form of a checklist. So in this next slide, I have a glossary of terms that I'll be using throughout, just for reference. But some of the more common ones that are things that you already know. We know what a ECC is. It's an exposure control category. OEL stands for an occupational exposure limit. Then we have the observed level of control, or OBSLC. We have the potential hazard ratio, or PHR. We have the required level of control. SVC stands for saturated vapor concentration. VP stands for vapor pressure, and VHR stands for vapor hazard ratio. In a separate lecture segment, I'm going to describe an Excel spreadsheet where this checklist is actually programmed in for you. So you can use these various rules of thumb in a very systematic way, that so the checklist is programmed in for you. So this is just a screenshot from that, but I'll come back and describe the actual Excel spreadsheet tool later on.